Hello everyone, so I'm going to be doing another video, this time on specific heat capacity. So you probably know something already, something about specific heat capacity already. I'm going to give you not only the definition but also methods that you can calculate or measure the specific heat capacity of substances. So there are three methods that I'm going to go through today. The first is the inversion tube experiment. The other one is an electrical method using a metal, and the other one the electrical method using a liquid. And under each of these three methods, you can see here I have the formulas where you can figure out the specific heat capacity or anything else, you know, if they ask you. So in the inversion tube experiment, I'm going to get that C, the specific heat capacity, is going to be equal to G, the gravity, times L, the length of the tube, and the number of turns, divided by the change of temperature. In the electrical method for the metal, C will be equal to the current times the potential difference or voltage times the time, divided by the temperature difference. And for the electrical method of the liquid, I'm going to have that the current times the voltage times the time is going to be equal to the addings of the masses, the specific heat capacity, and the temperature change of the two substances that I have there. So you will see the liquid in the container, okay, the capacitor, not capacitor, sorry, the calorimeter. So let me move on and explain each of these in more detail. And before that, I'm also going to remind you what specific heat capacity is, okay? So by definition, it's going to be the energy that you need to raise the temperature of 1 kilogram of a substance by 1 Kelvin, or then if you want 1 degree Celsius, because the change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. Meaning if I go up 20 degrees Celsius, I happen to go up 20 Kelvin as well. This does not happen with Fahrenheit, okay? With Fahrenheit, the difference is of 1 to, I think, is 1.8, something like that. This is for me to raise, as I told you, the temperature of 1 kilogram of that substance by 1 Kelvin or 1 degree Celsius without the change of state, okay? I know that some of you do chemistry, and in chemistry you may have heard in terms of 1 gram. That's fine. I mean, in physics we use the kilogram because our tables and our figures in the tables are going to be in the units of kilogram, but you know, it's just the same number as the gram, but you know, the difference of some zeros. So it's just, you know, it's not going to mean that it's wrong. You just need to make sure that when you're looking at a table, it either says per kilogram or per gram, okay? So this is the formula, and I'm showing you the formula in two different ways. So they mean the same, but it's just the ways that you can see. You can see as delta E or delta Q, both for the energy transfer, and it's going to be equal to the mass in kilograms. So the energy transferred, here it goes, is in joules, okay? It's going to be equal to the mass in kilograms. I know you can have it in grams, but you know, I'm just focusing on how we do it in physics, times C, the specific heat capacity. Now this is going to be in units of joules per kilogram Kelvin, or then kilogram minus 1 Kelvin minus 1, or then joule kilogram minus 1 degrees minus 1 degrees Celsius minus 1. Again, because the change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. Again, this is in kilogram. If your table shows grams, then you know it's different. But it's again, as I told you, a number. Sorry, a difference of some numbers. Okay, not the actual number, but zeros. And then theta or delta T is going to be the change in temperature, and again, it can be in Kelvin or degrees Celsius because the changes of temperature are exactly the same. Okay. Now, before I tell you as well about how you can actually do the experiments to figure out the specific heat capacity, let me just tell you a little bit more about it. So I have again a table here where the specific heat capacity comes in the units of joules per kilogram Kelvin. And I have different substances, stuff from water, marble, aluminium, concrete, all of these, okay? And if you look at the numbers, you're going to have some stuff like water with a very high specific heat capacity, concrete as well, and other substances like lead that do not have such a high specific heat capacity. So you can actually apply your knowledge of specific heat capacity for everyday situations. So if you have a substance like water and concrete, for example, that have a high specific heat capacity, then they are going to take a lot of time to heat up and a lot of time to cool down, because you need to provide with a lot of energy, right? But the good thing about it is that you can use them to store heat. So storage heaters, for example, they are made of concrete. You can provide them energy for them to heat up when the energy demand is low. Therefore, you know, you don't need to supply elsewhere, so you supply to the concrete. And then when you stop supplying the energy, it's going to take a long time for the concrete to cool down, because the specific heat capacity is so high. So you can use it as storage heaters. They are going to store heat and then slowly give the heat away. Okay, let me see what I said there as well. So land heats quicker, heats up quicker than the sea. Okay, oh yeah, I'm going to tell you about it in the next slide. The specific heat capacity of the sea water is greater than of the land, so more heat energy is needed to heat up by the same amount as the land. So the water in the land, they don't heat by the same amount if you give the same energy at the same time, and it also takes longer for the water to cool down. And this is actually going to be one of the reasons why you can get sea breezes, because think about it. The sun is heating up the land and the water exactly the same way. However, the land has a lower specific heat capacity, it heats up faster than the seawater. That means that I have warm air above the land, and cool air above the water. Now, as you know from physics, this is going to create a convection current. So it's going to make a movement where the hot air rises, because that part of the air loses density. Particles are further away from each other, so it rises. And then, as it rises, the cool sea breeze is going to replace the hot air, okay? So that means there is an empty space here, vacancy, so that warm air is going to go there. Now, the warm air is going to be on top of a cold temperature, so it's going to lose heat or thermal energy. The particles lose kinetic energy, they get closer together, and then the density of the air increases, making it to fall down, to sink. And then this whole cycle keeps repeating again, okay? And this is again because of the differences in the specific heat capacity of the sea or the water and the elements that make up the land, okay? So this is just some application. Now, how can I experiment and get some results for specific heat capacity? I'm going to tell you about 3 methods, okay? They are not the only ones, but I'm going to tell you about these ones. So I can have this inversion tube experiment. That's the tube here. I have some cardboard, I have some lead, small spheres of lead, and I have a glass rod where I can replace and put a thermometer to check the temperature change. I can keep inverting the tube every time, so going the tube and the spheres fall to this side and then invert again and so on. Now, when this is happening, I have gravitational potential energy from the height that you have that is going to be converted to internal energy as the object is going to fall down. I have an increase of kinetic energy and thermal energy, right? So this is going to make that there is a rise in temperature every time these lead spheres are going to reach the thermometer. So the temperature is measured initially and then after a couple of inversions. So the loss of my gravitational potential energy is going to have the formula of the mass of the spheres times the gravity times the height that they fell, so the length of the tube. For n inversions, the loss of GPE is going to be again the mass times the gravity times the length times n. So the gain of internal energy, because I know that I am having energy to be transferred to increase the temperature, is going to be the mass times the specific heat capacity times the temperature change. So because the gravitational potential energy is going to go to the internal energy, is going to be converted. Of course, this is not 100% efficient, but assuming that there are no losses of energy, I can make this formula equal to this one, cancel out the m's, and C is going to be equal to GML divided by delta T. Okay, so that's the first way that you can experiment and getting a practical result for specific heat capacity, and also this is how you demonstrate the formula. The second way is the electric methods using a metal. So I have a block of metal, okay, with a certain mass. I think that we are going to assume the mass is 1 and is insulated, so you want to avoid as much heat as possible to go to the outside. I have a 12-volt electrical heater, okay, so here it is, and then I have a thermometer to measure the temperature difference. So due to electricity, I'm going to have the heater that is going to give in heat or transfer the heat to my solids, okay, to my metal. So the energy supplied is going to be the power times the time that I apply this energy. So it's going to be I, the current, times V, the voltage, times T, the time. Okay, because this is how I get my circuit. That's the power. I have an ammeter, voltmeter. I can figure out what the power is, and I'm multiplied by the time. Okay. And here it is, power and heating time. I is the heater's current, V is the heater's potential difference or voltage. Now the gain of internal energy is going to be again the specific heat capacity. So, sorry, not the specific heat capacity, but the energy transferred to increase the temperature. So it's going to be the mass times the specific heat capacity times the temperature change. So again, making that the electrical energy supplied is equal to the gain of energy, I'm going to get the formula for C, and that's going to be I, the current, times V, the voltage, times T, the time, divided by delta T. And again, you can have the M there, the mass. I think this is because the mass was 1 kilogram for the block, but you can have the mass in there, okay? Finally, the last method is the electrical method, but using a liquid. It works just the same. I have a known mass of liquids. I'm going to use electricity to heat up this liquid, okay? And I use a 12-volt electrical heater. But remember that now a liquid can flow, so I need to have it in a container, okay? So I'm going to have in a calorimeter, which is going to contain my heater, okay? So this is very simple. It's going to be exactly the same way as the electrical method. How do I figure out the specific heat capacity? The electrical energy that I supply is the same. So it's power times the time. Therefore, it's going to be the current times the voltage or potential difference times the time that I apply the heat, okay? The energy to heat up the liquid is going to be the mass of the liquid times the specific heat capacity of the liquid times the temperature change of the liquid. Remember that the liquid is not just insulated, it's inside of a container, and this container is not made of the same thing as the liquid, so it has its own specific heat capacity. So my energy to heat up the calorimeter, I have a problem with this word, is the mass of it times the specific heat capacity of it, or the container, times the temperature change. So now I need to think that I'm not only heating up this liquid, I'm also going to heat up this outside, okay? And there are going to be some energy transfers while they are not in thermal equilibrium. So assuming that I lose no heat to the surroundings, which obviously is assuming the ideal condition, I have that the IVT, so the current times the potential difference times the time, is going to be equal to the adding of the mass of the liquid, not the adding, well, the adding of, yes, sorry, the mass of the liquid times the specific heat capacity of the liquid times the temperature change of the liquid, plus the mass of the calorimeter times the temperature change of the calorimeter times the specific heat capacity of it, okay? So this is how you can then figure out the specific heat capacity. Quite simple, okay? I have here some questions. All of them have answers in there. Yep. And these are all to do with specific heat capacity. So attempt the questions if you want. The answers are already showing. And as always, if you have any questions, just let me know. Until then, have a happy and healthy life, okay? So see you in the next video. Bye.